Hello, thank you for attending the first of two sessions on wildfire simulation under climate change. I'm happy to welcome you all and a great lineup of speakers. We'll have the 20-minute time blocks for each speaker. We have three speakers in this first session, followed by an open discussion section at the end. So I encourage you, if you have detailed questions, we might have a chance to discuss those as a group at the end. And to start things off so that we don't get behind, I am really happy to introduce our first speaker, Dr. Carleen Hay from the company Risk. She'll be talking about a new exciting approach at modeling wildfire under climate change. Thank you, Carleen.
Hi, thank you. Sorry, I'm mute there. Thank you so much, Alex, for inviting me to speak today. It sounds like a really interesting session, and I'm looking forward to the discussion afterwards. I just want to acknowledge my co-authors, Karen Riley, John Rowe, and Evan Kodra. And this is work that we've done on sort of really looking at Northern California wildfires and trying to better understand how the risk of wildfires in that area might be evolving under climate change. So not a surprise to anyone here. Northern California has been home to many wildfires over the past few years. And of course, these wildfires are not a new thing. We can look here at historical wildfire perimeters, looking back to the sort of pre-1950s and so forth in the yellow regions here, and then up to sort of modern times the last few years in red. And so obviously wildfires have been existing in Northern California for decades and centuries, but really the question is what's going to happen moving forward in time under the threat of climate change. If we look at projections of temperature changes, specifically for California, we can see that multiple scenarios are projecting increases in temperature over time. Here we're looking at the previous IPCC's projections, RCP 8.5 in red and RCP 4.5 in blue. What you'll notice is that both projections are increasing over time. And what's really important to notice is that the projections don't really diverge until about 1950. So we're really setting ourselves on a fairly certain path over the next 2 or 3 decades. And so what I want to tell you about today is the approach that we've taken to try to really understand how these projected changes might affect fire risk in the California area. One of the overarching themes that I'm going to talk about today that's related to this technique that we've developed is to really try to use all of the data in the method that it performs the best. And so the sort of underlying theme of this work is to try to use weather observations, try to use reanalysis data where appropriate, and try to use global climate models in the best way possible to sort of look forward in time. So I'm going to walk you through those techniques and then show you some initial results that we have from running our fire simulation model with both our historical data and our climate condition sort of future data. Okay, so here's a little geography for you. So we're looking in Northern California, specifically at Pyram 31, which is sort of the Napa-Sonoma region. You can see that zoomed in here on the bottom right. What we want to do is we want to use on the ground weather observations whenever we can. And that's because we believe that the station observations are really best at capturing sort of the local variability in the day-to-day weather on the ground. And so if we have that data, we want to use it. So what we're going to do is we're going to take the 2 closest stations to the center of that pyrome, which are given here in the blue squares. And we're going to merge those 2 together to create sort of one time series of weather station data over time. Now, of course, no data is perfect, and so there's going to be gaps in that weather data. And so what we do to sort of eliminate that problem is fill in any of those data gaps using reanalysis data. For this study here, we're going to use North American regional reanalysis data taken from 2 different grid points shown by the red triangles here in the bottom pyrome. So what that actually looks like is here we're showing what our temperature data looks like and what our precipitation looks like from those merged station and merged reanalysis data points. In both these frames here, the gray is our station data. You can see that there's some gaps over time. That's our missing data. And then in turquoise, we have our reanalysis data from those two merged grid points. What you'll notice is that the temperature data agrees very well between the reanalysis and the station observations, whereas the precipitation data does not agree very well at all. You can see what you would expect in the station data, right? You see large precipitation events over time, whereas the reanalysis data has a much more muted effect. It almost looks like sort of a background drizzle over time with no real sort of precip events happening. And so what we want to do is we want to make sure that as we fill in those data gaps, we're correcting for those known biases in the reanalysis data so we can get sort of our best estimate of what the weather might have looked like on that day if the station had been recording. So the way that we do that is we model the relationship between the station observations and our reanalysis data using all days when we have overlapping data. We do this by just modeling a very simple linear relationship where parameters are estimated from any overlapping historical data that we have between those two types of data sets. To give you an idea of what that looks like, here we're looking at temperature on the top frames and precipitation on the bottom. Our x-axis here is our reanalysis data, and the y-axis is our station data. And both these two frames on the left-hand side, that red dotted line is simply the one-to-one line. So if the reanalysis data agreed perfectly with the station observation, in this ideal world, then all those black dots would fall perfectly on that red dotted line. If we look first at the temperature difference, we can see that as we thought, the station data and the reanalysis data agree fairly well, with the station temperatures being slightly higher than the reanalysis temperatures. However, when we look at the precipitation, we can see just how much that reanalysis data is underestimating the precipitation that's happening on the ground. All those black lines lie really far above the red dotted line. So what we're going to do is we're going to fit both of those relationships to that linear trend, and then we're going to use that relationship to essentially get an estimate of what we think the station data would have looked like on those days where it's missing. So the result of that sort of filling technique gives us these two curves here on the right. This is what we call our pseudo station data. Well, you'll notice that there's no longer any data gaps over time, sort of both very complete records. But most importantly, anywhere where their gaps have been filled in using this technique, we can see that it really sort of looks a lot like what the station data looks like. So for example, in the bottom frame on the right with the precipitation, we see large events happening throughout the time, and we sort of eliminate that sort of drizzle constant rain effect that we saw in the reanalysis data. So these new complete pseudo station data become our historical input data for our fire simulation model, and they span an entire 30-year time period from 1990 until 2019. Okay, so now we have our historical data. And the next thing is to create our weather data under a future climate. So to look at future climates, what we do is we turn to global climate models put out by the IPCC. Here we're looking at average September daily temperatures at that same location near Napa and Sonoma. The orange line is the estimate from the North American Regional Reanalysis data, and the 7 blue lines are different global climate models. They're covering the historical time period from 1980, through to 2005. And then they're going out with RCP 8.5 projections out to the end of the century. What you'll notice is that none of the blue lines match the orange line. They don't match in terms of the long-term trends, and they don't match in terms of the variability. And so we're stuck with this problem of how do you sort of pick the best GCM or best projection if they're also bad at actually reproducing the past. And so what we've developed is a way of overcoming this problem to really make use of these GCMs in the manner in which they perform the best. And that's in terms of their long-term projections or long-term trends. So what we're going to do is we're going to eliminate all of that interannual and multi-decadal variability that's in the climate models. This is where they are notoriously bad at getting the local characteristics. And so we're going to fit each one of these curves to a 30-year running mean, and that will smooth out all of that variability. Then what we're going to do is we're going to apply the statistical technique that we developed, where we will actually model that bias that we see historically in each one of those GCM models. With that model of the bias, we're then going to do sort of a Monte Carlo simulation where we'll randomly sample from that model to get thousands of bias corrections that we can then use to get thousands of possible futures under the same scenario. Once we have thousands of possible futures, we can then get statistics on what that distribution might actually look like. Okay, so here's sort of what that looks like. The red line here is our 30-year running mean of the North American regional reanalysis data. The dark black lines, those are the smoothed original GCM projections. And then all of those gray lines in the background, those are our thousands of simulations that are bias corrected. What you'll notice is that the gray lines collapse around that red line in the historical time period. And then we see a spread in values going forward through the end of the century. What we want to take away from this are long-term trends. This is what we think the GCMs do best. And so what we're going to do is fit a linear trend to each one of those gray lines and look at the distribution of those trends across our thousands of simulations. And so that's what we're looking at here on the right. We're looking at the distribution of all of those trends taken from those gray lines. In this case, we have our red line here on the right, and that is our median trend in average daily September temperatures at this specific location in Northern California. We do this same statistical modeling technique for every variable of interest at a monthly resolution. So we get statistics on average October daily temperatures, average November daily temperatures. We look at monthly relative humidity for the month of January, February, et cetera. And then we also look at precipitation extremes for every single month. What that gives us in the end is a time series for every single month of the year with what we call a change factor. So here we're looking at our change factors for mean daily temperatures, which again are at a monthly resolution. And they tell us how under a specific climate, we might expect the variable of interest to change. So what we're saying is that in the month of January, under a 2060 climate, we would expect to see about a 2.5 degree Celsius increase in temperature. What you notice in this case is that temperatures are increasing throughout the entire year, with the peak increase in temperatures happening in sort of late summer, early fall, out of about 3.5 degrees Celsius per year. So what we get is we get a similar time series like this, again, for all of our variables of interest. So we get an idea of how temperatures will change every month, how relative humidity will change every month, and how our extreme precipitation is also expected to change. What we can then do is take these change factors and modify our input weather data. So what we want to say is we have 30 years of historical pseudo station data, so that filled in weather data. If that same 30 years of weather happened under an RCP 8.5 2060 climate, what would that day-to-day weather look like? So what we're going to do is we're going to take these change factors and modify those historical inputs. So we're going to say for every day in January in our historical weather data, let's modify it by this change factor of about 2.5 degrees Celsius. For every day of August temperature in our 30-year historical time series, let's modify it by this change factor of 3.2 degrees Celsius. So we modify all those 30 years of historical inputs using these change factors that we've derived for our 2060 climate. We can zoom in to sort of see what that looks like. So here we're looking at April to October of 2005. We're going to focus in on the blue and the green lines here. The blue is our pseudo station data from the historical time period. So that filled in data. We're looking at temperatures on the left and precipitation on the right. And then our green line here is that climate conditioned or our 2060 weather data. So because we're simply modifying the historical time period, your day-to-day weather is very similar, right? If you have a drop in temperature, historically that will happen in the future. If you have a rain event in the historical record, you have a rain event in the future. what you'll see is that there's sort of a shift in what those values actually are. So when you look at the temperature, you can see that difference between the blue and the green lines in sort of the summer months. And you notice that that's a larger difference than what you see in sort of the spring and the fall months. And that's because that change factor was largest in that late summer, early fall. This is even more obvious in the precipitation data. It's a little harder to see, but we're looking at sort of the light blue dots compared to the dark green dots. If we look in the spring months, what you'll notice is that the light blue dots are higher than the green dots. That means that we're projecting a decrease in the amount of precipitation during these extreme events during the spring months. Whereas in the fall, what you'll see is that the dark green dots are slightly higher than the blue dots, indicating that we're expecting more extreme precipitation during these fall months. And so we now have sort of two complete time series, one from that historical time period, and then one from our sort of climate condition 2060 RCP 8.5 climate. Once we have those two time series, we can then feed those into our fire simulation model and really start to assess how that wildfire risk is going to change. So we're going to do that first by looking at changes in our energy release component. So here we're looking at mean daily ERC. Again, our light blue is our historical ERC, whereas our dark green is our RCP 8.5 2060 values. The blue dashed line is the 80th percentile from the historical record. What you'll notice is that the two lines agree fairly well in sort of the winter months, with the largest differences happening as you would expect in sort of late summer, early fall. The biggest change that you'll notice is the widening of that peak under this sort of future climate scenario, and also a taller peak in that sort of times around August and September. So what you're seeing here is a lengthening of the fire season and a potential for more extreme fires when they happen during that peak fire season. So what we do now is we put this into our fire simulation model. We start with our historical burn probabilities. Here again, we're looking at just this that same area around Napa and Sonoma. Here's the annual burn probability coming out of our fire simulation model. Across the entire region, we get a mean annual probability of 0.79% and a mean large fire size of about 7,500 acres. These agree very well with historical estimates. And we can then use our curve calibrations from this historical run to generate a new burn probability map driven by that sort of climate conditioned weather time series. Okay, so here are results from that. The first thing that you notice is there's a lot more pink here, right? Very few regions where you have sort of dark green or zero burn probability. What that translates to is a mean annual burn probability across the region of 1.58% and a mean large fire size of about 10,600 acres. What we do is we call that sort of our climate impact. And what we're showing here and suggesting is that under RCP 8.5 2060 climate, we would expect the mean burn probability to double, and we would expect the mean large fire size to increase by about 40%. So quite a dramatic change in just under 40 years. So sort of putting that all together, obviously we expect wildfires to continue, and it looks like they're going to get significantly worse for that region. But really the main takeaway that I hope to leave you with is that we really want to use all of our data sources in the manner in which they perform the best. So we believe that the station data is best at capturing that local spatial and temporal variability. So really getting that day-to-day weather. But the reanalysis can actually be very useful in helping to fill in any gaps in that record, especially if you first bias correct it by using those relationships between the station reanalysis data for when they overlap. In this case, we used North American regional reanalysis data, but you could substitute in any of your favorite reanalysis data to perform that sort of filling step. When we look forward in time using GCMs, we really want to try to use GCMs and the manner in which they perform the best. And that's really looking at long-term trends. And so once you sort of put all of that together, you can really start to assess how your wildfire risk might change over time under any sort of climate condition that you're interested in. And thank you for your time.
Okay, hello everybody. My name is John Kim. I'm a session co-organizer. I am stepping in here to introduce our next speaker, Alex Dye. Dr. Alex Dye is a faculty research associate at Oregon State University and a longtime collaborator of mine, as well as many of you in the audience. So Alex, you're on.
Hello, thanks again for joining the conference and the session. So I'm going to step in and give a talk of my own that follows nicely from Carlene's talk. You'll notice in this session, they're all the approaches are FSIM centric, so different ways to use this fire spread model. FSIM to approach questions of climate change and wildfire. So this has been we're working in Southern California here with a group, including also Karen Riley from the Rocky Mountain Research Station, who was on with Carlene's project on the last talk, Pang Gao from UNC Wilmington in North Carolina, John Kim from the Western Wildland Environmental Threat Assessment Center, and Larissa Yoakum from Utah State. So it couldn't have happened without all this group working together. So I want to just kind of showing our study area and what some of the results look like that we're trying to interpret. We're using the MACA Met data, downscale GCM climate data, and essentially we're taking a subset of all of those GCMs that are available, an 8 GCM subset, and running this model FSIM on a set of contemporary climate conditions across those 8 GCMs, and separately running it for a set of future scenarios that represent the mid-century, the mid-21st century under the RCP 8.5 climate change scenario, and then looking at the deltas, the changes between those two scenarios. So we're not doing a kind of an iterative approach that builds it over time. We're looking at this chunk of time in the future, this chunk of time in the contemporary, and then taking the difference between those and see how that difference varies spatially, how the difference varies between GCMs that have different climate characteristics, and seeing what that can tell us about future changes and fire probability and fire spread, but also what that can tell us about the underlying GCM itself and how that can change your outlook in the future. FSIM, so Carlene was using this, and John following me up is also going to talk about this model. It's a fire spread simulator developed by the Missoula Fire Science Lab in Montana for the Rocky Mountain Research Station. So most of the credit all of the credit goes to them for developing this and working with us and helping myself learn it and figure out what it can and can't do. But it essentially simulates the ignition, probabilistic ignition, and then subsequent spread over fires within a region, and it's calibrated over a set of historical fire statistics, so historical fire ignition locations, sizes, and fire frequency over a set region that we refer to as a pyrome, which also is what Carlene was working in. So you got to see a nice map of different pyromes across the Western California, Northern California area. And so it's first the model will be calibrated to match historical fire probability, fire size, and fire frequency statistics. And then once that is done, you can change certain things with the climate inputs to kind of do a sensitivity of how that affects your baseline, how that deviates from your baseline calibrated fire model. And that's what we've done with future climate inputs in this study. Specifically, the energy release component, ERC, is the main variable that FSIM interprets climate as. So this is just a measure of the fuel, the energy at the flaming front, and the 80th percentile for the region is the specific one that it uses, just based on the historical relationship between that number and large fire occurrence and spread. So throughout this presentation, I'll look at a lot of these climate scenarios and changes based on that 80th percentile ERC, because that's the one that really matters to this specific model. Here's the two pyromes that we're working in. So this is roughly Pyrome 33, we're going San Francisco down the coast, and then Pyrome 34, we're looking like Santa Monica down to San Diego and the border. And we've been taking a single MACA metadata grid cell from this spot where the red triangle is. And so that is what has all of our information from that we've calculated energy release component from, and that we're using to develop our historical baselines for the GCMs and also our future RCP 8.5 scenarios for each GCM. Then this blue border, that's where we allow ignitions to ignite, and so they can spread into the pyrome, so you're not getting weird edge effects and such. And this is more or less how an example of how in this project we calibrated the model to reflect some historical conditions. So in the gray curve, you're just looking at average fire counts per month on the left, and then average fire size per month on the right. And that gray curve is showing those statistics from the 1992 to 2015 period, which is what we have at the time we enacted this project, is what we had robust historical data for. And then that blue line is what our modeled calibration. So this is kind of what we're shooting to meet that gray curve as close as possible. And as you can kind of see right at the bat, it more or less matches it, but there's some interesting deviations. I particularly point out the fall season and the southern part, which is the far right figure. So you have seen a couple of really big historical fires in October, which are basically Santa Ana winds coming through and just driving humongous spread of these fires. And that number there's a bump in the fall that we see in the blue line, but it's not quite that extreme. So that's something to kind of note that I want to note as I continue in this project is are we getting that very, very important, one of probably the most important aspect of the Southern California fire regime in the fall and winter months. So we selected a subset of GCMs. There's 18 available off the shelf from the MACA metadata data set. And we selected a subset of 8 of them to run from each pyrome. And we selected a subset because FSIM takes about a week plus to run each time. And so if we do that for each pyrome, even if we're doing 8, that's 8 historical GCM runs times 2, and then that's 8 future runs times 2. So you're already at 32 runs, which is several months of simulation time. So even doing 8, I think, is a pretty cool and detailed subset that we were able to do. And we selected 8 of them to incorporate this range of bias and future changes with regards to that 80th percentile ERC marker that I mentioned earlier, because we can calculate that before running the model. And we wanted to make sure we got, because there's a large range of bias, we wanted to make sure we captured a model that represents that full range of bias historically. And then we wanted to also make sure we captured the full future range from even models that are below this black horizontal line that indicate a decrease in ERC in the future, as well as the ones that indicated an extreme increase. So rather than selecting the best, the quote unquote best model that matched the historical conditions and showed, the most extreme future, what we were really interested in this project is, because we don't really know why each of these GCMs exists along this horizontal continuum. And so we don't really want to try to figure out why. We just want to see what happens when you use that type of a model, one that has a high and low bias, one that has a big future change or a big future decrease. So that's that. We selected on these 8 models, and I'm going to show you some example results from those three GCMs. But if I'd encourage you to hold on any detailed questions about this specific slide until you hear John Kim's talk. After this, he's going to kind of discuss the bias and change situation in a little more detail, and is more knowledgeable on that than I am. So if you take this IPSL CM5ALR GCM, and you look at, so this is not showing the future burn probability. What this is showing is the difference between the future burn probability and the baseline burn probability for this IPSL CM5ALR model. And you can just, it's interesting with, so if we think about the other graph in the northern pyrome, you see some blues indicating decreases, and then in the southern pyrome, there's a lot of increases in the red. And if you go back to that graph I had showed, you can kind of see where there's the IPSLA has a much shallower increase in the pyrome 33 on the left, but the same GCM has a fairly steeper increase on the right. So there's some spatial differences in the changes and biases of these, even within the same GCM across the different pyromes. So if we look at another one, this is MIROC5, which was the most extreme projected increase in 8th percentile ERC days for the southern pyrome 34, which is why you see a bunch of dark red here, but also a pretty strong increase in the north. And an increase of 0.01, so that's about like an increase of an annual burn probability of 1%. So you could think that's your average. If you extrapolate that to 10 years, a 1% increase per year is basically saying you have 10%. Your chances of having a fire in 10 years is 10% more likely. And then here's one where we had a decrease in both pyromes. So BCC CSM1-1M actually had decreasing ERC 80th percentile days by mid-century. And it's complicated as to why. ERC incorporates things like precipitation. And so several of these models have precipitation increasing, and if the temperature does not likewise increase that number could decrease. And then also for the burn probability maps, timing matters, because we think about I mentioned earlier, the Santa Ana fire season, which is essentially mid-September to January now. So the timing of when these fires might occur, if a lot of fires are happening if you got a lot of future fires happening in October, November, December, which I can say is definitely the case with this last slide on the MIROC5. That could be one compounding factor that creates these giant increases in burn probability, versus if you're increases in ERC and fire occurrence are happening in months, like just say April through June, when the fire spread isn't as severe based on the winds and such. Even just an increase in some of the climate variables may not have the exact same effect. This is kind of how FSIM, the 80th percentile ERC versus burn probability. So this is just after we've gotten the results in terms of burn probability. This is just to kind of reiterate that point that FSIM responds pretty robustly to the 80th percentile ERC days. So generally, as you increase the number of 80th percentile ERC days in a year, you get a fairly statistically significant increase in burn probability, which is how it should be, but we wanted to check that. This is something I'm going to pass on, and I could bring that up more in the discussion, but I want to go back into this map, which I showed at the start. So this is the mean of all those 8 GCMs. So you got a chance to see three examples of those 3 example GCMs. And so if we take the mean of all 8 of those maps that look like those 3 that I showed you, we get something that looks like this. So overall changes, we see changes, positive changes, increased burn probability. But if you do that same thing for the minimum, you see that there's a lot of uncertainty there, a lot of decreases potentially. So GCM showing a decrease. And then if you look at the maximum, you can have pretty extreme maximums. So there's a very large range in those deltas that we see. But if you look at the mean overall, it shows an increase. And so there's a map of the variability. Okay, and so as a recap, this is another new approach to evaluate the within GCM changes in simulated burn probability, that's BP. Most of the GCM simulate increase, but not all of them. And there's a large range of burn probability deltas between the 8 GCMs that we selected, as well as some spatial variabilities between the northern pyrome and the southern pyrome, and some interesting questions related to the historical bias and the future change. And that's going to be all brought up in John Kim's talk, which is happening next. So that sounds like a great time for me to go ahead and wrap up. And grab a quick drink of water before I get John Kim on here. All right, John. Next up, we have John Kim, who's a research scientist with the U.S. Forest Service, Western Wildland Environmental Threat Assessment Center. John is going to talk about bias and change in climate change fire modeling. Thank you, John.
Thanks, Alex. If you can't see my screen, please wave or holler. As you could kind of guess from all the introductions here that, a lot of us have collaborated on these projects. And so my talk is going to be about a rather hot topic that has come up repeatedly within our groups, and we've discussed and debated very vigorously about this issue. And the issue is when we're using GCM-based future climate data to drive the FSIM fire model, how much bias is too much? And my collaborators are all listed here: Alex Pangao from UNC Wilmington, Ken Riley, and Larissa. So I want to give you just enough information to set the stage for the debate that's going on. And my intent is not to really dive into the results per se, but to talk about sort of this philosophical underpinnings of the study design and what the implications are. So everything is based, that we're talking about is based on FSIM, which takes gridded inputs to represent the landscape. And then the model runs on a data time step, it generates weather, and then it ignites multiple fires, spreads them, and applies a suppression algorithm. And it does that for 365 days a year and repeats that sort of Monte Carlo style for 10,000 years to generate kind of a statistical summary of what's going on in the landscape. As with the other talks, we have been focused on studying these two regions in Southern California. And the thing that I want to point out here, there are two things. One is that you take the future climate and you convert it into ERC streams before it goes into the model. So that's one point. So the model does not see temperature and precip and humidity directly, it just sees it in terms of ERC, and it gets the wind speed and direction. The other point is that when you apply, the conventional way of applying FSIM is to take a region and you pick a weather station that is, at one location usually within that region to pull the data from, and then the future climate data is also generated based on the patterns that you see at that one weather station. So the point there is that there's one weather station per region. And in our study, we have divided Southern California into two regions. So one way that it has been, future simulations have been done before is using what we might call the delta method. And let me see if I can illustrate that. So in panel A, you've got climate data, and the black line represents, so it's time going from left to right. The black line represents some observation weather stream. And GCM1 might have a bit of a high bias, and GCM2 might have a low bias. And with the delta method, which is illustrated in panel B, is how that does that is to take the delta, that is the anticipated projected change from the present to the future, and it applies that to the observed time series from the weather station. So then you wind up with just a single simulation for the present, but you have multiple simulations for the future. With the way that we've been approaching it in the current phase of the study is what we might call the per GCM method. And in that method, we take the GCM, the weather as the GCM produces it from present day into the future, and we run it twice, once in the present using the GCM's version of the present, and then once again using the GCM's version of the future. So for the present period, you have the baseline run, which is the observation-based run, and then you have another set of runs that are based on the GCM's version of the present. Another way to conceptualize how all this, how the two methods compare is that with the delta method, which is diagrammed on the left side, you have one observation, one simulation based on that observation run, observation data, and then you create future runs, and then you make inferences about whether fire increases or decreases or spatial patterns of fire change by comparing the future simulations against the one reference present day run. With the way that we're doing it in this phase of the study, in the per GCM method, which is diagrammed on the right, we have multiple present day simulations, one per GCM, and then we have multiple future simulations, one per GCM, and we make certain inferences by comparing within a single GCM. So the problem arises because with some GCMs, they, as you've seen in the prior talk, there's some significant bias. So for example, in the left panel here, you've got the historical run FSIM output of burn probability based on the observation data. The middle map is the present day run based on GFDL, ESM2M, GCM. And then on the right is the difference between the two. And there's some significant bias. And by the way, this is all using the MACA downscale data, not raw GCM. Some GCMs have low fire bias in that when you compare the middle map, which is the GCM-based present day, versus the observation-based reference run, there's a low bias. And then some get it pretty close. I wouldn't say just right, but it gets it pretty close. Another way to look at the bias is to kind of lay out all of the ERC values that gets fed into the model. So from left to right, we've got days of the year, 365 days of the year. The first blue stripe is the upper pyrome, the upper region that we're simulating. And the blue is all the ERC days that are below 80 percentile. And then the colored ones are the ERC days above 80 percentile where fire is ignited and spread. And the main point here is that the bias is not just a monolithic bias, but that it varies over time and varies between the pyromes. So the really, to kind of trace things backwards, the question is, what we ran these models, we get to the output, and then we're scratching our heads saying, can we interpret? How do we interpret the results? And what about the bias? So in the bottom panels, we have the simulated future changes in annual burn probability. So on the left side, we have GFDL, the ESM2M, projecting future decrease. And then we're asking ourselves, well, but it started with a certain bias. Does this affect the way that we should interpret this? So for example, the fact that GFDL, ESM2M based results project a decrease, is it because we started with a high bias that we see a decrease? Or is that a quote unquote, a real signal? If you look on the right side, that's HADGEM2 ES based results, and that one, at least in Southern California, it has somewhat of a comparable high bias, but it projects a future increase in burn probability. So it does not appear that having one type of bias doesn't necessarily dampen future response. So I wanted to I laid out some of the pros and cons of the per GCM approach that we're using. The pros might be that we are using the signal that has greater fidelity to the GCMs, the weather that the GCMs are simulating, that it's retaining some of the sub-monthly signals in the time varying signal that it has. And the cons might be that that the bias kind of throws a wrench into the interpretation of the results, and it makes us wonder whether that's going to be an issue. Let's see. A little unsure how I'm doing. Okay, I think I'm doing okay on time. And we also wonder whether having a warm bias or a hot bias or a cool bias might by itself directly affect the way that FSIM responds. So for example, like I said, if a GCM starts with a very warm bias, does it somehow limit the amount of increase in burn probability that it is able to simulate in the future? And then there's another big con is the complexity. You wind up with many more simulations, which takes more time and more analysis. And the part that I kind of like thinking about are some of the mitigating, or some might call it complicating factors. One is that bias does not appear to correlate to projected changes. And really the fun part is that there are so many other sources of uncertainty that come into play here. And I'll get to that part in the following slides. So here's what I mean by retaining the submonthly signal. This is just a conceptual diagram, not actual data. But on the left side, you have a plot showing future seasonal ERC curves, and it is going to have a time variant signature that is, or the futures will have time variant signatures that are relatively close to the observed time varying signal, because we just applied the monthly deltas to the observed signal. On the right side, with the per GCM method, we let the GCM have whatever time varying signal that it has. So it's going to be it's going to have a more varying signature. We saw a version of this in the prior talk, but the thing that I want to point out is something I've already said, which is that if you plot the historical bias of the GCMs along the x-axis, and you plot the projected change in ERC, which also drives much of the variance in FSIM behavior along the y-axis, there's not a very clear one-to-one line. In other words, you can't say because a GCM has a high bias, it's going to project low future change, or vice versa. The GCMs tend to be kind of all over the place. And so the part that I think actually is rather essential to think about is that we are kind of somewhat you might say boxed in, or we're working with a particular modeling framework here, where we have a model that covers a large area, but the conventional way of doing it is to take a single weather stream from one place to represent the driving weather for the entire region. But there are so many other uncertainties. So that's one way of representing weather to simulate, but there are so many uncertainties that are relevant here. So, for example, we have different climate change scenarios to consider, which can result in very different outcomes. The differences among the GCMs, as you saw in the prior slide, create a huge difference. And then there's the selection of the weather station. There's the calibration issue, how many of the parameters that we tweaked, how sensitive the model is to those. And then there are things like the model formulation, such as whether the model's ability to simulate wind-driven fires really may swamp out all of the other factors that we are scratching our heads over. So this is an illustration of what I mean by the GCM variability. So, along the x-axis, we are really, we've debated vigorously about the importance of this bias, which has about a 22 range in terms of the average number of days with ERC greater than 80 percentile. But the projected change among the GCMs is like 59 days. So, maybe we have to kind of let go of the bias a little bit and worry more about the GCMs. Here's a diagram illustrating the importance of the choice of the weather stream. So here are 3 possible weather stations that we could have chosen for the northern pyrome that we are simulating. And depending on which of them you choose, the peak ERC month could vary. So in conclusion, I guess we can say that the bias does appear to be significant, and the bias of the GCMs make creation and interpretation of the future more complex. But the bias does not seem to predetermine the outcome of the models, which I think is good. I believe that the bias, while it can be somewhat confusing to look at, we also need to take it in the context of all of the other uncertainties that come up. And then I think having some fidelity to the GCM signals gives us an opportunity to learn about the way that the model behaves. And our intent in wanting to talk about all these issues is actually to invite other people's thoughts about whether it's more prudent to try to preserve today's time varying weather signature going into the future, or does it make more sense to explore the variability among the GCMs? And I think all of that really goes back to the way that you understand what these future projections are. And there's actually quite a lot of debate about what the RCPs are, what the projections are. And I guess my time's running out, so I'll just conclude it by saying that I believe that future projections are just one plausible scenario. It's not a prediction, and the metric that we should use for whether to use something or not is whether it's plausible or not, and whether by running that model we can learn something from it, rather than saying, is this an accurate prediction of the future? Because there is no accurate prediction of the future, at least not if you run it based on the RCPs, because the RCPs are not predictions. Thank you very much for listening, and to all of our collaborators and data providers.
All right, thanks, John, and thanks, Carlene, for some great talks. At this point, we have several minutes, 20 or 30 minutes available to have an open-ended discussion on the 3 talks we saw today, or about fire modeling with climate change, or FSIM in general. So I'd like to invite anyone to turn on their video and sound capabilities, and we can have an open discussion with the audience, and you can ask questions directly through the Zoom conference, I believe. That's how it would work. Or you could continue to place questions into the Q&A chat on Whova, and I can field those myself and relay them.
I do see one there already. Alex, would you like me to read it?
Yeah, go ahead and read it. Kick it off.
This is from Greg Dillon, who of course works with me in Missoula, and he also said he had to hop off. So I will loop him in on whatever we talk about for the answer. So he said, thanks for these presentations. A key to the future projections of burn probability in FSIM is how many days in that future weather stream are above 80th percentile ERC. Can you clarify if those percentiles are calculated based on historical observations and then held constant, or do you calculate percentiles from the historical GCM data or the future GCM data? And that's probably for everybody.
Yeah.
I don't know if you're going to rock scissors. Anyone can take that. Who's presented so far?
Yeah. So for us, for the second presentation that you saw from me, we calculated that 80th percentile ERC based on historical observations and then kept it constant for all historical GCM and all future GCM scenarios. That way it gave us something to evaluate back to so that we could calculate some sort of change that was interpretable. If we calculate it again every single time, then there's no you can't relate it back to what you're trying to calculate the change from. And I'll also say, since I breezed over this in my presentation, that the historical observations that we have used for our project are based on the gridded data set of historical weather. And that's just because it's on the same it's designed to be on the same spatial scale and temporal scale as the MAGA-MET data sets that we wanted to use for climate change evaluations.
I wanted to, oh, sorry, go ahead, Alex.
No, I could let Carlene or Karen add on to that.
I was going to
sure. Oh, go ahead, Karen.
No, Carlene.
Yeah, I was going to say, we do the same thing in terms of we use our compute the 80th percentile from the historical observations, and then that drives the sort of future simulations.
The footnote I was going to add is, I think this was referenced in the presentations, but if we didn't drive it home with a sledgehammer, that 80th percentile is a significant benchmark in FSIM, because FSIM only predicts large fires, or that's what it's endeavoring to do. And so it only ignites those if the day is above 80th percentile ERC, and they only grow on days that are above 80th percentile ERC. And so if it dips below that level, the fire can sit there for a while, but then it might go out. And that ERC is, it's basically a fire danger rating and tied to fuel moisture. So those are your drier types of days, just to summarize that a little bit. Does anyone else want to add?
Well, I'll just add, while we're waiting for the next question, because 80 percentile is it's a relative metric, right? So if we were to calculate new 80 percentile in the future, then that would just make a higher threshold for fire occurrence, right? So the fire behavior wouldn't change very much from present to the future, because you're just raising the threshold.
And that 80th percentile, there's nothing really magical about it, but in the recent historical period, that is a point at which we see number of large fires and acres burned goes up exponentially around that 80th percentile. So that's just been kind of the conventional wisdom from the field about where that benchmark should be fixed. So if ERCs get a lot drier in the future, like John said, we don't want to be moving that benchmark, I don't think.
Karen, could you say something about where, what type of ecosystems that applies, best in? Because I wonder if there are certain ecosystems where that, the 80 percentile doesn't have the best correlation to large fires.
Yeah, no, I think that's a good question. And there might be other folks here that want to discuss with us too, but ERC is really commonly used in the Western US, and it seems to have a really tight correlation with number of large fires and area burned. It works really well in the West, in summary. I have heard, I haven't studied as much, but I have heard from folks working in the Southeast, and Ping might want to weigh in here, that maybe ERC doesn't work as well in that part of the world. And oftentimes fire folks there use something like the Keach-by-Rim Drought Index instead. The nifty thing about this is you can check this out really easily if you're using the Fire Family Plus software, which is where a lot of us build the input files for FSIM. You can look at that relationship and see some summary stats of how well it works for your part of the world. So Ping, I don't know if you're sitting there and you want to say anything else.
Yeah. So can you hear me?
Yeah.
Yeah. So I asked the Kevin about these fire indices, and I think he said if he only pick up one of the index, he would still pick up a ERC. So, and if you remember the scale plot we did when we examined the pattern in Southeast, it still shows the strong relationship of the ERC with the larger fire occurrence. I think that's my guess. I think the relationship may not be as strong as in the West, but I think it still works in Southeast.
Thanks, Ping. I'm curious too, if people don't have specifically questions, I think this is also a great time to discuss. And we still have, it's kind of a shame this discussion slot didn't come at the end of this session, because there's a lot more presentations coming. So if people want to give us sneak peeks or bring up any issues that are on their mind, I think this is a fine time to do that too.
I could do a plug for on Thursday. There's a fire circle session that will basically be a continuation of this discussion, but also roping in the fire management modeling group that Nick Skoronsky and Kevin Heers are putting on. So that could be something if questions come up throughout the week or after the session that follows this one. We can have some discussion there as well. So this isn't the last chance to bring your question up. But I could pose a question that might be interesting to some people. For Carlene, I think Carlene's talk is quite interesting, and one thing that I was curious about, and that people might be curious about, is who your audience is with this project, and maybe a little bit about what risk is as a company, which might provide us a little bit of a different perspective on some of the agency and academic based talks.
Yeah, sure, I'd be happy to. So Risk is a for-profit company, and we look at the intersection of the fixed income markets and climate change. So specifically municipal bonds and climate change. So quantifying for any sort of entity that issues debt. So that could be like the city of San Francisco that's trying to raise money to improve roads. It could be a hospital system that's trying to raise money to build a new wing, a charter school that's trying to raise money to build a new elementary school. And so each entity or any school or city that sort of tries to raise money is associated obviously with a geographic area that you can physically map out. And so what we do is we quantify the present day property value at risk and GDP at risk. due to natural hazards, things like wildfire, hurricanes, inland flooding, and then we quantify how that risk will change over time. So that the idea is to give investors a better idea of how, under climate change, that financial risk may change. And so that's where the wildfire modeling that I've done along with Karen and our collaborators to sort of really quantify how that risk might change over time to some sort of arbitrary geographic area that we can define with specific boundaries.
If I can follow up with a question for you, Carling.
Sure.
So, as you've made, you shared that really cool map of the fire. I think it was burn probability for California. So, from the beginning to the end, as you made all these various decisions to get to that map, what do you think are some of the components that were really the key decisions that the end result is the most sensitive to? So if you had made a what different decision could you have made that would result in a very different burn probability map? I mean, are there some components that stand out?
So I guess for us, the biggest component is probably the climate conditioning part, sort of how we modify our input variables. Because we are looking at across the country a multitude of different hazards, we developed a climate conditioning approach that was applicable to all the different hazards, so not just wildfire. And because of our target audience, we have, at this point in time, have chosen to look at just at medium projected changes over time. But of course, I'm a scientist. I think that spread is almost more important than just that median change. And so obviously, if we had sort of focused instead on sort of upper or lower tails of those changes, you could get very different results. But outside of the academic realm, it's not there yet. So I'd say for us, that sort of was, the most important thing of sort of deciding which path to take. We're really focusing on the climate change component. We ultimately sort of take some geographic area and aggregate up. So we aggregate over sort of some mean boundary, whether it's a school district or a municipality or a county or a state. And so some of the smaller differences that I think you would see in some of the fire simulation models become a little bit less important because we're aggregating up and looking at sort of like changes over time. This is also all being fed into sort of a lot more layers on our end, because we're actually looking at, okay, now how do those wildfires impact the property? And so that, there's an estimate of what property is sitting on that land and what the replacement cost is and who works there and who lives there. So there's so many layers on our side. And I think some of those upstream layers might have a bit more uncertainty in some of the fire modeling.
Okay, thanks. So any other questions from people listening in? I can pull up a few more that I've been writing down myself, but I wanted to make sure to give the audience a chance. There's about 10 or 15 people in the audience listening in. They have any input?
Can I ask a question for John?
Yeah.
No one else? I'm curious, John, have you looked at any of the new CMIP6 models in terms of what the biases look like in those models?
No, the short answer is that I have not, but
yeah,
I have been reading about, how the RCPs are created, what they represent, what the SSPs are, and there's a lot of debate about whether even RCP 8.5 is really that plausible. Yeah, I think it's just interesting. It's interesting how, where the RCPs come from, who created them, how, using what modeling method, and what was their intent. And then, there's been a lot of debate about how the scientific community just because it's out there takes it and runs with it as if it's a prediction, or people compare RCP 8.5 and 4.5 as if like 4.5 is somehow a mitigated version of 8.5, and that's not quite right. And anyway, so yeah, no, the short answer is that I have not, and we have not. We're, the way that we're doing it, we're a little bit dependent on the downscaled products. So as far as I know, actually, I take that back. I just became aware that there is a next DCP-30 downscaled product for the CMIP6 GCM outputs, but as far as I know, there is no Maca version, and the Maca version is better for us because it has more weather variables, whereas the next DCP-30 data set has just temperature and precip. What do you think? Are you guys thinking about using SSPs to drive future simulations?
We are. We are not, I'd say not in the next year. But yes, we do want to sort of move over just to sort of keep with the latest, the latest science. I don't think it would make a huge difference, to be honest. But I think that, that we will start to sort of incorporate that moving forward.
I could toss a question to Karen Riley if there's a moment. Well, Karen, based on everything that's been discussed here, if you could wave a magic wand over the whole FSIM future simulation process, from the whole field of GCNs, of downscaling methods and products, choice of raw stations, a station or multiple if you want to create a synthetic one. Which of that process component would you wave that magic wand over so that you have the most satisfying future simulation? In other words, which one of those is causing me the biggest heartache in terms of looking at the output and saying, that doesn't sound plausible to me?
Boy, I don't know if I have any heartache, because I was just thinking what a nice cosmos all of these approaches make this morning, and how much they contribute to the understanding of the overall problem. And I think, Mark Finney, who wrote the FSIM model, he's really fond of producing some data and some outputs so that you can really look at them and sift through them and understand, what issues various uncertainties might be driving. So I thought this morning for me was such a nice example of that, of really getting some data on the table and being able to look at it. And there's so many things that would be nice to have. I think maybe a crystal ball would be the best, so we know what the future climate actually would be. But short of that, I'm also interested too in the new spread equations that Mark and myself and others are really trying to incorporate in FSIM that are going to be physics-based, because right now we're running off of a set of empirical equations which do fine, and that's why they've stood the test of time. It's based on the Rothermel equations, and those have been there since, oh gosh, what is it, the 70s, I think. But we're working toward really a physical understanding of heat transfer and how flames carry fire from fuel patch to fuel patch. And so we're thinking about the next generation of models, and it's really going to turn things on its head of how we're not going to have the fire behavior fuel models anymore, the Scottenberg and 4D. We're probably going to have models that look at arrangement of fuels and gaps and clumps. So I'm really looking forward to that. But I guess if I could pick one thing, it would be that crystal ball, John, for the future.
That's interesting. I mean, short of having the next generation model, I'll answer my own question and see what you think of it. I think I would love to have two things. One is somehow a way for the model to take into account the different weather and wind field across the entire region, because it's so highly variable. because right now we're driving with just one weather station, one weather stream. So that I would love to have that. And then number two is especially for simulating fires in regions where wind-driven fires are very important. It would be nice to have something that can better simulate synoptic scale large wind events like Southern California or the Pacific Northwest, where we just had a huge set of wind-driven fires. I'm not sure that those are necessarily the largest contributors of model uncertainty, but just throwing them out there.
Yeah, no, and I hope the newer version helps with winds a little bit, because it's going to have, I think it's a Weibull distribution, if I remember right, for the wind speeds. So in the past, you could only get wind speeds that were observed, and now the model will be able to give you higher wind speeds than what has been observed. So that might help with the latter, hopefully.
Alex, do you have any comments on that? What would be on your wish list for magical improvements to the process?
Yeah, all of the above. I think I would be, one thing that I would like, and this is probably just because of where my head has been the last year, is just a better understanding of what it means to have a GCM that doesn't really mirror the whatever historical observation is. Like, so just a much more robust understanding as an entire scientific community of what that means, why that happens, and whether or not that propagates into the future. And I think that's a lot of the discussions that John, Kim, and Karen Riley and I have been having, which is why that's sort of at the top of my head. Why does it matter, and why does it matter, and what are the consequences of having different GCMs or different climate projections that say different things, and how do we translate that into fire, specifically into fire, because that's what matters in these projects.
I'm going to poke at our audience members again, because I wonder if there's anyone who has anything to add to that. Any thoughts on that?
Well, while we're waiting for something from the audience, I'll just bring up a point that that has come up in my conversations with Alex that I forgot to mention in my talk, which is that there is this idea that what weather is a chaotic and stochastic system. So the way that we have observed recent historical weather is just one of many possible ways that it could have happened. So the recorded weather at a single station, according to this philosophy, this is may not be the only way, is not the only systematic feature of the weather system, but it's one manifestation of the weather that could have been.
I find that to be kind of a mind-blowing thought, John, and of course I think it's true. So that maybe has implications for whether we consider the recent observed weather sequences to be in some way sacred, since they could have happened in some other fashion, certainly.
If I can ask Carly another question. So Carly, I'm sorry if I missed it, but I think your current analysis is focused on mid-century, is that right? About around 2050?
So we look at actually, well, we do every decade going out from sort of out to 2060. That's sort of the time horizon that we're most interested in. The work I present today, which is which we're working on publishing, we're focusing on 2060 as sort of this 40-year future time horizon. But of course, 2060 is like a 30-year time period centered around 2060.
And then which RCPs do you
we do both RCPs, 4.5 and 8.5. But for this project, we're focusing on 8.5.
I see.
Yeah.
And then you mentioned calculating, results for small areas. Is there, well, my first question is, do you calculate, say, changes in burn probability for small municipalities? And if so, do you have concerns about taking the modeling result and focusing on a small, when the model is calibrated for a large area, do you worry about drawing conclusions about small portions of that modeling domain? Because we have that problem with, especially with vegetation models, where you calibrate the vegetation model for a large area, and then if you focus on a pixel and say, oh, that's going to change, that brings up some discomfort.
We don't, maybe we should. We sort of a whole process of, obviously we're running FSIM at the PIROM level. We get sort of our burn probabilities across the whole country. We then convert everything to a 100-meter grid because that's where we do all of our modeling. And then we aggregate from that level based on where we're looking at. Often, you have bigger problems like in towns or cities based on like whether things actually burn and how you sort of propagate that. So I think there could be cause for concern. I think we're really focused on changes over time. So I think that helps a little bit because if something is sort of maybe a little bit off in our future run, it's probably a little bit off in the historical run. And so that sort of helps a little bit. But yeah, as we've said, there's uncertainties in every part. So I think you have to almost pick and choose your battles.
Absolutely.
In sort of the space that we operate in, most people are not running fire simulation models, and they're looking over much broader areas and making sort of general statements about what's happening at a state level. And so, for our purposes, we're doing much more advanced modeling. So we think we're moving in the right direction. But I totally agree with you. Every time you make an assumption, there's a possible ripple effect. But usually Karen asks us the hardest questions, so and usually she's on our side, so that's good.
It's true. I've been really impressed with what y'all are doing, and it's fun to see it coming to fruition.
Okay, there's technically 10 minutes left in the discussion. It's a good time to ping the audience for anything else that they would want to know about, even things like why are we using FSIM, or just basic questions that we couldn't go into detail in the short time frame of talk. So doesn't seem
also in the community tab of the Whova interface, I saw that there were attendees from kind of all over the world. So if there's anybody here who is interested in or applying some type of fire modeling to other ecosystems around the world, I would love to, have a discussion about that. if you click on the community tab, you can, I think it's the community tab, you can see different flags from all over the world. Oh no, maybe that's just, those are the options. Okay, I guess people haven't, that's a question that we could answer.
That's been one of the silver linings we've found to the virtual platform. And I think we on the AFI board, we've resisted having any portion of our conferences be virtual in the past. Like I think IAWF has moved to hybrid conferences earlier than we were. But we feel that the in-person gathering is so valuable that we haven't done that. And we've kind of feared that if we offer a virtual option, that's going to cause every employer in the world to say, why should I pay for you to go there? So we have been resistant to that. But what we are finding about that international involvement is now that we're virtual, there is a lot more. So a lot of the people we've been really, really hoping to reach, we're now seeing included because they don't have to travel halfway around the world to get here. So that's really been a silver lining. And I feel like we're probably not going to go back. We're probably always going to have a hybrid component. Hopefully employers will understand that face-to-face is really, really valuable too. Did you have any follow-ons, Alex? Sounded like you maybe had a short list there. Did you get through them all?
Yeah, so I had a question. I targeting John, but more or less just everybody. So one thing I've noticed in this talk of the different assumptions that you might make with modeling and biases, et cetera. There's this concept of like, does the model perform well or does it not perform well, with the implication being like, is it good or is it bad? And I was wondering if John and others had any thoughts or insights into sort of changing that narrative away from good and bad versus useful or not useful, and sort of how to make that connection between, is it really bad in the sense of, it's just an awful piece of thing to use, or is it bad in a way that's useful for a different meaning? So.
Well, I think that's a great question, Alex, and a really great one to bring up because, and that's exactly kind of the thing that I've been thinking about. If you go back to, how these climate change scenarios were created, and the RCPs, for example, and the GCMs that simulate those RCPs. I think that would change a lot of people's ideas about what's good and what's bad, because they were not created to say this is an accurate prediction of the future. This is a kind of a somewhat consistent, plausible, plausible future, but not probable. They're not saying it's probable or not probable. They're just saying it's plausible. It's things sort of, all the various components fit together to create this picture of the future. But I don't think any of the creators would say there's a 90% chance we're going to go there or 10% chance we're going to go there. So given that that's the case, plausibility, I think, is really the criteria we have to use to say whether something is good or bad, and not is it accurate. I mean, you can say that if you're talking about creating a picture of what we have already observed, then you can say, well, that's a good, replication of what we've observed or not. But of the future, we could only say, is this plausible or not? And then for scientific research, I think another metric is this something that helps learn something about the way the system works? So to me, those are the two ways, the two ways to shift or to kind of reframe the good and bad labels. So yeah, we can say it's good or bad, but why something is good, why an approach is good, or why a model output is good is dependent on, one, is it plausible, and two, is it something that we learn something from? How's that strike you?
Yeah, that sounds great. We got about 2 or 3 minutes if Carlene or Karen or Peng or anybody have an add-on to that.
Yeah, I mean, I think John's right. None of these models were meant to be a prediction of the future. And so I think it's important to use them and think about what questions you're trying to ask with these models, and make sure that whatever result you obtain, you're framing it in the right way to not make, an overconfident conclusion that this is the future. There's a lot of problems with the GCMs. Some of them are known, some of them are unknown, some of them are unavoidable. And so, we're bad at predicting the weather 4 days in advance. So anyone who thinks that you can look at a GCM and determine what the weather is going to be like on, November 22nd, 2041, that's not how they're meant to be used. So I think keeping all that in mind and really sort of looking at the sensitivities of these models is really important for evaluating how they're going to sort of feed back into processes like wildfire.
Okay, great. From my perspective, that was a fantastic discussion and session. So that wraps it up for time. And I'm going to toss it back to the producer, Jessica, she has an announcement to make. And then I'll wrap it up. And if you're around, show up for the session right after this on more climate change and wildfire simulation. Be 5 great talks in that one. So thank you all.